Hello, astronomy class. This is my first video for doing this. I hope it works. I'm in my classroom. I can show my screen up here. Looks to me like you can actually see the screen, which is pretty cool. What I'm going to do is go through chapter 1 and highlight what I think is the most important stuff to know, the kind of fun stuff to know. This is an overview chapter. Almost everything we're going to do in more detail later. But, you know, there's a few things that it's good to get out of the way now, really get these things down, because we're going to be using these words and stuff a whole lot later. So I'm just going to go through a lot of the chapter and highlight some things. I suggest you read the whole thing thoroughly on your own. It's good reading. You learn a whole lot. But again, I just want to highlight the most important things. Okay, so you should have downloaded this as a PDF file, the OpenStax astronomy book. You can have it on your phone, your computer. It's all free, and it's really good. I mean, it's like a top quality textbook that they made for free, which is awesome. So, all right, so it's called Science in the Universe, a Brief Tour. So again, this is just an overview. They have a nice picture of galaxies colliding here, which is kind of cool. Let's see if I can make this work. So we scroll up, there's a chapter outline, nature of astronomy, like what is astronomy? Nature of science, laws of nature, numbers in astronomy, tour of the universe. Yeah. So I'm going to go through a lot of this kind of fast, but you can read it on your own. So first off, there's this introduction here. Yep, you can read that on your own. There's something that's out in space. Any guesses what it is? What is this thing? Some big planet, right? It is Mars. This is this big valley, Valles Marineris. It's pretty famous. In the planets class, we talk a whole lot more about the details of planets. We're not going to go through a whole lot of that in this class, but you should know the planets, and that's one thing you should know. Okay, so there's Mars, lots of good stuff. There's a really cool picture of a supernova exploded. We'll talk a lot about stars exploding in this class. You'll know exactly what this is. This happened, the star exploded in 1054 because people took records of it. It's pretty cool. Okay, so what is astronomy, right? Seems like we should know what astronomy is, and they define it as the study of objects that lie beyond our planet Earth, so outside of Earth. I guess study of the Earth is geology, so it's not astronomy, it's geology. So outside the Earth, which is a lot of stuff, right? That's pretty much everything out there is astronomy. Planets and stars and galaxies and the universe and how it all started. How it all started is called cosmology. The cosmos is another word for everything out there. So the cosmos and the universe are kind of the same thing. It's a word for everything out there. So cosmology is a study of how everything out there formed. If you're a cosmologist, you study how everything out there formed. So I think they use that word here, cosmos. Thought I saw it out here. Well, anyway, you can find it. Carl Sagan's famous series is, called Cosmos. We'll watch some of those videos because it's like the universe, everything out there. Okay, moving on here. The nature of science. We'll talk more about science in general later. You guys have all taken science classes before, so you kind of know what science is all about. They talk about models and how you learn from observing, and anyway, we'll talk about all that stuff later. You can read this on your own. Let's see, what else here? Yeah, making predictions, hypotheses. You guys know all about this. So, one interesting thing is, for astronomy at least, which is kind of cool, is it's definitely an observational science. You can't really do an experiment with building a star in the laboratory. You can't build a planet in the lab, right? You have to actually just look at things. It's purely about looking at things. We've sent spacecraft out in the universe, out into the solar system, to look at things better. They don't like kick it to see how it works. So it's pretty much an observational science. You can't do an experiment necessarily. You just have to look and look and look and get lots and lots of observations and data, and then try to figure out what's going on. They also call it a historical science because you look back at the history of the universe. The further something away it is, the older it is. We'll talk about that later, but so you kind of get a history of the universe by seeing how far away things are and by looking at things. So yeah, so it's both observational and historical in a sense. It's not experimental. You can't really do experiments. Okay, that's kind of cool. So lots of good stuff here you should read. Okay, that's about applying the laws of nature. You guys have studied the laws of nature before. The rules that nature seems to follow to the universe. And a really big thing they talk about here, okay, as far as astronomy goes, is that there is an assumption, which seems correct, that all the laws of nature we know on Earth apply to the universe too. So we figure out gravity on Earth. Oh, I bet gravity works this way on Pluto and works this way on the Andromeda Galaxy. It's not obvious it should, but it seems like it does. When we apply the laws we learn on Earth to the universe, it makes sense. It seems to work. So that's a pretty big step to say that what works on Earth works way out there, you know, way out there in the sky. Maybe it doesn't have to be true, but it sure seems to be true. So that's a pretty big deal. So that's different from like other sciences, that the laws of nature we have here work everywhere else, which is kind of cool. Okay, numbers in this class, we don't do a lot of math. You can take astrophysics, and it's heavily mathematical. If you really want to study astronomy, this is like just kind of a survey course at the University of Washington. It's kind of for non-majors, non-science majors. Though a lot of science majors take it, and they decide they like astronomy, and they go into astronomy. But it's not supposed to be a hardcore science course. It's just supposed to be learn a lot of cool stuff about the universe, and maybe do a little bit of basic math that you should know. So we're not going to do a whole lot of math, but some stuff, we will do a few things that, again, most of you should know, and it's good review if you don't like scientific notation, because there's a lot of huge numbers in astronomy, right? The distances are big, so you kind of have to do a little bit with that. So we do some stuff with scientific notation. Numbers we use a lot are like light years. A light year is how far light travels in a year. Light goes so fast, light travels so fast that to measure, you know, how far it goes in a year is really, really big distance. So it's a huge number because light travels so fast. So instead of using big numbers like in meters or something, just say a light year. And that's a lot easier than saying some gigantic number in meters or feet or miles or something. However, it is good to know some basic numbers, like how fast light does travel. I'm like most Americans, we think in miles and seconds. Well, everybody does seconds, fortunately, in minutes and hours. That's one good thing. Everybody uses that for time. But we know other countries, every country besides the US uses meters, kilometers, and we use miles and seconds. So you should know the speed of light. They probably mentioned it in here somewhere. But okay, it's 3 times 10 to the 5th kilometers per second. So it says it right here, which is the same thing, and this is the number I remember, 3 times 10 to the 8th meters per second. So that's a 3 with 8 zeros, right? Scientific notation, a 3 with 8 zeros. A lot easier to say 3 times 10 to the 8th than to write 3, 1, 2, 3, 4, 5, 6, 7, 8. If I saw that number, I'd have to try to like count up the zeros or something. It can help if you put commas. 300, looks like it's 300 million, 300 million. But just say 3 times 10 to the 8th meters per second. Now, that's in meters. I think in miles. I like the number, because I'm American, 186,000 miles per second. Because I can relate to that. 186,000 miles a second. That's how far light goes in 1 second. Imagine how far it goes in a year, right? And they actually say that. Which makes a light year, which is 9.46 times 10 to the 12th kilometers. I know 10 kilometers is 6.2 miles, so that's about 6 times 10 to the 12th miles, 6 with 12 zeros miles. Let's see, that would be 9 zeros is billion, so trillion, about 6 trillion miles is a light year, which is some big number. You know, it's huge, doesn't really make sense to me. But this number you can think about. So for instance, the Earth circumference is about 25,000 miles. The one trip around the Earth, if you were to go around the equator, about 25,000 miles. So in 1 second, light goes 186,000 miles. So let's see, it goes 25,000, 50, so 1 trip, 2 trips, 75, 100, 125, 125, 150, 175, and a little bit more, right? So it goes 1, 2, 3, 4, 5, 6, 7, a little over 7 times. I usually say like 7.5. It's close enough. The other thing we talk about numbers in astronomy, close enough is usually good, unless you're actually doing astronomy where it's important you know the exact number. Yeah, close enough gives you a good idea. So about 7.5 times around the Earth in 1 second. Light can go around the equator in 1 second 7.5 times. That's pretty good. Or the other way I think about it, which makes sense to me, is the moon is about 240,000 miles away. Okay, 240,000 miles away is the distance to the moon. So when the astronauts are on the moon and they are talking to the Earth, and the Earth is talking to them with radio waves, which travel the speed of light. All light waves, radio waves travel the speed of light. Light goes 106,000 miles in 1 second, so it took more than a second to get there. It took about you do the math, they say it's about 1.3 seconds. So if you're to talk to somebody on a moon base, you send a message, they get it 1.3 seconds later, they hear it, they send something back, you get it 1.3 seconds later. So it's like about a 3-second delay. So it's kind of like talking on a radio, a walkie-talkie, not like talking on the phone, because they're too far away. So if we're going to talk to anyone, you know, the moon and further out in space, you can't just kind of talk and interrupt each other and stuff. You got to say your thing, you know, wait a little while till they hear it, and then they say something, you hear back. It's not like having a conversation. Okay, so this number is kind of good to keep in mind. Again, I find it more useful because I think in miles than the kilometer number. Okay, so that's some stuff with numbers. So you should know those numbers. So when you're doing this, again, I think I would take notes because I'm going to emphasize the most important thing. So I just have a sheet of paper. I'm not going to grade your notes. I'm not going to grade your notebook. I suggest you just learn to keep one. In most college classes, that's kind of the way it works. You're just expected to learn the stuff, and you do what you want, but it better work for you. So I suggest you write these things down. It'll just help you. So you don't need to write a lot down. You don't need to copy the chapter or anything. I'm just going to, again, emphasize the things I really want you to know. Like these numbers I wrote down here, you should know. Okay. So, yes, so light years, how far light travels near, big distance. All right, let's move on here. That's a really cool picture. All right, they like throwing all these cool pictures. This is the Orion Nebula. You can see that through a telescope with like the school's telescope. But unless you have a really good telescope, you don't see the colors. Through the telescope that I have, you can kind of see some clouds and stuff, but it's more black and white. Your eyes don't see color very well. It takes way more intensity of light to see color. And so your rods in your eyes that see in black and white that don't see color are much more sensitive. So they fire off first. So if it's kind of dim, you just see things in black and white. It takes bright light to see colors. You need a really, really good telescope that covers a lot of light to see this. But that's what good telescopes see. So they do see colors like that. So it's kind of cool. Okay, so there we go. They give some stuff here about, you know, big numbers and stuff. So yeah, so we'll talk about some other ways to think about how big is a billion, you know, because yeah, numbers in astronomy are so big. It's like try to think of ways to make sense of it. So okay, here they do some math with light years and stuff. I'm not going to really emphasize the math part. We'll do some math for sure, but let's skip that right now. Okay, consequences of light travel time. Okay, this is one big deal, one big thing, right? So light travels really far in a year, and so you say how far away something is in light years. The moon is too close to call it light years. Typically, the solar system, there are other units to use because everything in the solar system is not a light year away. But the closest star, Alpha Centauri, which we'll talk about more later, is about 4.3 light years. So when you see a star in the sky, it's not a planet, you see a star, it's the closest one, and you can't see that one from Leavenworth. You have to go down south to see it. Maybe from Hawaii you can see it. Well, you can from Hawaii. But Alpha Centauri is about 4.3 light years away. Okay, so it takes light 4.3 years to get it, which means when you see it, which you can if you go south, it's really bright. Not the brightest star, but it's the closest one. When you're looking at it, you're seeing it as it was 4.3 years ago. Okay, so you're looking at what it was. You can't see it now. You can always see it in the past. And so that's why they say it's kind of like a historical science. You're looking at the history, kind of. You're looking back in time. We're seeing things 4.3 years ago. Who knows what happened to Alpha Centauri now? Maybe it blew up. They don't think it will, but so you're looking, when you look in the universe, when you look through a telescope, you're looking into the past. People call them like time machines. You're looking back in time. The further away something is, the older it is when you're looking at it. Who knows what it looks like now? And it might not even be there now. So when we say that Alpha Centauri is 4.3 light years away, well, it was 4.3 light years away 4.3 years ago when the light we see came from. Maybe it blew up. Maybe it's something moved away really fast. We don't know. Now, no one thinks it did, but some things are moving. So when you see things, you figure out their distance by looking at their light, and we'll talk about that a whole lot. How do they know how far away things are? And that's often called the look back time. I mean, we say distance. I always say distance, how far away it is, because most things don't change their distance that fast. But if it's really far away, then really what you're saying is, well, the look back time is 100 light years. When we look back at it, it's 100 light years away. Who knows where it is now? So when you say something's distance, do you mean the distance when you're looking at it, or the distance it was? Anyway, it's confusing, right? So the point is, you're looking back in time when you see things, because things are very far away. So they talk about that here. It's kind of cool. That's one cool thing about astronomy. So telescopes, yep, takes time to see things. There's a Hubble telescope, which is in orbit. Okay, the universe here. So let's take a tour of the universe. Okay, so first off, we live on this planet here. Hopefully you know that by now. This is the Earth. Kind of cool. Okay, so that's where we live. So there's our home base. So, okay, now, here are some things we should know. So write this down. I'm going to write you need to know something about the Earth. And I'm going to, again, approximate is good enough. Okay, unless you're going to study the Earth in great detail. Approximate numbers are good enough. Okay, so we're just going to round off. And I'm going to use miles. I think in miles best. You probably think in miles best. You can always convert to kilometers. So we're going to do stuff in miles here. So here's the Earth. So first off, how wide is it? Okay, so on the average, okay, so here's the width. It's about 8,000 miles wide. And I always write miles as MI, or I spell out miles, but who wants to write more than you have to? If you put M, it looks like meters. Okay, so MI for miles. So it's 8,000 miles wide. Therefore, the diameter is about 8,000 miles. So it's about 4,000 miles to the center. If you want to go to the center of the Earth, you got to dig a hole 4,000 miles deep. Okay, so keep that in mind. Center of the Earth, 4,000 miles deep. Now, what is the circumference then? I said earlier it's about 25,000 miles, right? If you walk all the way around the Earth, about 25,000 miles, and that's because the circumference is pi times the diameter. 3 times 8,000 is 24,000, but it's 3.14, a little bit more. So it's approximately, so to say approximately instead of equals there, you just make a squiggly equal sign. So pi, it's about 25,000 miles. Good enough. If you're actually going to travel around the Earth and you want to know precisely what it is, then do better math. But good enough, right? It's a good round number. About 25,000 miles all the way around the Earth. Okay, so that's one thing you should know, okay? The diameter of the Earth, 8,000 miles. Okay, we'll stop there. We're not going to worry about more details of the Earth. But 4,000 miles in center, 8,000 miles across. Okay, now, how about the moon? So I think we get to, I'm going to erase this stuff here, so write those things down or memorize it, 8,000 miles. Circumference about 25,000. So let's go down here then. And this is a picture to scale. This is a scale picture. If this is the Earth, then here is the moon. Now the moon is about 1/4 as big as the Earth. Not exactly, but close enough. Okay, so the moon's diameter, and so we're going to put a little arrow here, but the moon's diameter is 1/4, which is about 2,000 miles. Okay, so the moon is about 2,000 miles wide. That's a number you should know. Now, this is to scale. Okay, if we put 4 of those moons there, see if I did that just about right, put 4 of those moons, be 1, 2, 3, 4. right? 4 should fit across the Earth. So they did a pretty good job here. You can look in, it might be hard for you to see it up here, but look in your own computer, look in this book on your own phone or whatever. About 4, that's pretty good. And it turns out if they did this right, there should be about 30 Earths. If I do 30 of these, which I'm going to get tired and not do it, but if we go all the way here, the last one, we should fit about 30 in between. Okay, so the moon is about 30 Earth diameters. Instead of writing Earth diameters, I can just write ED. Can you see that? It's kind of, yeah, maybe you can see. I'll write it on top of the white. It's a lot easier to see on top of the white. So this distance here is about 30 Earth diameters. Earth diameters away. The Earth's diameter is about 8,000 miles. So it's about 240,000 miles away. And earlier I mentioned that number, 240,000 miles. The moon is about 240,000 miles away, which is about 1.3 light seconds. It takes 1.3 seconds for light to get there. So this is about 1.3 light seconds. Takes, there's a C in there, light seconds. Okay, so that's kind of cool, right? The moon is 30 Earths away. A lot of times in picture books and whatever, they put the moon really close because to do it to scale, you have to first, they got to be really small to put on a piece of paper, and it's this far away. I mean, that's not very interesting to be in a children's book or something. It's just too far away and too small. The moon is pretty darn far away. 30 Earth diameters away, 240,000 miles. It's way up there. It's amazing that gravity from the Earth can still pull it, right? Keep it going in a circle around us. It makes this big circle all the way around us, 30 Earths away. Yeah, it's amazing, a lot of gravity. And actually, it's not a circle, it's an ellipse. We'll talk about that a whole lot later. It's not always exactly 240,000. It gets closer, it gets further. But again, roughly on the average, yeah, it's close enough, 240,000. Okay, that's good stuff to know. Let's move on here. We'll do a few more things. Let's say, okay, we know it takes the Earth a year to go around the sun. Which is about 3 times 10 to the 7th seconds, roughly, not exactly. So they put that number there. It goes about 66,000 miles per hour. On our trip around the sun, we go about 66,000 miles per hour. That's kind of a fun number to know. Okay, so let's write that down. The velocity of the Earth around the sun, velocity of the Earth around the sun is about 66,000 miles per hour. So every hour we go 66,000 miles on our trip around the sun. After a year, we make one trip. You could do the math, figure out how far that is. But that's just kind of cool. We're going fast. We're going really fast. Okay, this picture. This is one we're going to write down a lot on. Okay, so be ready for this. Okay, so there's our picture. I'm going to erase this. All right. First, this is to scale for size, obviously not distance. We're not this close to the sun, we would burn up. The planets are not all lined up like that. They're really far away from each other, but the size is right, okay? So if this is the size of the sun, which is too big to fit on here, the size of the sun, then this is how big Earth would be. This is how big Jupiter would be. Jupiter is obviously a lot bigger than the Earth. Okay, so the sizes are right. And then they also put, like, here's Pluto. Pluto is the smallest planet, but it's not a planet anymore. It's a dwarf planet. Here's some other objects, Haumea, Makemake, Eris, some other objects in the solar system are kind of like Pluto, which is why Pluto is not really a planet anymore. So, they're all small. Okay, Ceres is pretty small, but again, this does not scale for distance. Okay, first, one thing you should know, and in planets we do a lot more details, but you should know the order of the size of the planets. Okay, anybody takes astronomy should know just basic things about this planet. Obviously, Jupiter is the biggest. Give that a number 1. Obviously, Saturn's second. Uranus is third. Neptune is fourth. Uranus is just barely bigger than Neptune. Neptune's actually heavier. Neptune's denser, but Uranus is bigger. So that's real easy, right? Start with Jupiter, 1, 2, 3, 4. And then Earth is next. Earth is the biggest terrestrial planet. It's the biggest land planet. These guys are all gas. You can't stand on them. So Earth's pretty good, right? It's the biggest terrestrial planet. So it's the 5th biggest planet. And then Venus. Venus is like our sister planet. It's close to Earth in size. And then Mars is 7th. and the Mercury's eighth. Mercury's about the size of the moon, a little bigger, but Mercury's, they say, is kind of like the moon, about the size of the moon, looks like the moon. It's the closest planet to the sun. Now, the other thing, okay, so first order of the planets is like that, just real easy, 1, 2, 3, 4, order by size. 1, 2, 3, 4. Earth is next, so it's a fifth one. Then Venus, then Mars, Mercury's the smallest. That's not hard to memorize. It's just good stuff to know for the rest of your life. And okay, then you should know this order. You should just know which is the order of the planets like they have here. The way that a lot of people memorize it is by memorizing a sentence where the first letter of each word helps you memorize the planets. The one that I've always heard is my for Mercury, very for Venus, educated for Earth, my very educated mother for Mars. Now, there's one problem here, right? There's two M's. You have to know Mercury's closer. You just have to know that. Because or Mars is not close or something, because there's two M's. But so my is Mercury, very Venus, Earth is the third planet, educated mother, just for Jupiter, served us, and now there used to be Pluto, right? I always keep Pluto in there, so just served us 9 pizzas, and pizzas is for Pluto, because Pluto's cool, and some people actually, there's actual real talk about making it a planet again. Who knows, but we'll just include Pluto in it. So my very educated mother just served us 9 pizzas. So us is Uranus, served, Saturn, just, okay? So that's how you can memorize the order. Just remember my very educated, and remember M is for Venus. Now, let's do some more. We don't need to worry about how big the planets are, just the order, how big they are. Obviously, Jupiter's huge. Jupiter is actually bigger than all the other ones put together. If we took all the other planets, smushed them all together, Jupiter is bigger and heavier than all the other ones. A whole lot bigger and heavier than all the other ones put together. Even though Saturn looks like it's practically the same size, it's actually not very dense. So really, it should be a little bit smaller as far as mass and everything. So if you put them all together, Jupiter's still way heavier. So Saturn's not quite as big as it seems because it's not very dense. Okay, last thing we'll do in this video. You should know that the sun, the size of the sun, it's about 109 Earths wide. 109 Earths. So if this is the size of the Earth, we put 109 of those, we'd get all the way across the diameter of the sun. So the sun's diameter is about 109 Earths diameter. Okay, that's a fun thing to know. It's about a little over 100 times bigger than the Earth as far as width. Way heavier. But the volume is 100 times 100 times 100. Okay, way, way, way bigger in volume, but 109 Earth diameters wide. And here's another really important number. The distance from the sun to the Earth, remember this is not to scale, but if we did it to scale, the distance from the sun to the Earth is about 93 million miles. 93 million miles. I usually write million, but whatever, 6 zeros. 93 million miles, which, because that's a good number to use for our solar system, because light years, Pluto is not even close to a light year away. So we might as well just use a different unit. So this is called 1 AU, 1 astronomical unit. So an AU is an astronomy unit. They call it astronomical unit. And it's really good for our solar system. It's not good for the universe. The universe is too big, but it's really good for the solar system. So 1 AU is the distance from the Earth to the sun. And then we can measure everything else in the solar system by AUs, by Earth-Sun distances. Now, it's not always exactly 93 million miles. We get closer to the sun. We get further from the sun because we go in an ellipse. We go in an oval shape. But, you know, it's close enough. So 93 million miles. Oh, by the way, which is about 8 light minutes. It takes 8 minutes for light to get here from the sun. That's a cool number. It's actually a little bit less, but it rounds off to 8, closer to 8 than 7. So we just say 8 light minutes. It's a little bit less than that, but it takes about 8 minutes for light to get here. When you look at the sun, the light that hits you from the sun, it's 8 minutes old. It left the sun 8 minutes ago. If the sun exploded 5 minutes ago, we wouldn't know yet, you know, until boom, but it takes 8 minutes. So, okay. Now, Last thing is we're going to do AUs of all the planets, which is surprisingly easy. Okay, there's all the way to Pluto. It's actually not that bad. So we know Earth is 1 AU. That's the definition of it, right? Now, turns out that Mercury, the closest planet, Mercury, and I'm going to write them on top of it here, hopefully you can read it, is about 0.4 AUs. Okay, 0.4. Yeah, you can read that there. So Mercury is 0.4, Venus is 0.7, and Earth is 1. Okay, Mercury on the average is 0.4 AUs, Venus 0.7, 1. Now, those numbers are kind of hard to memorize, except that they're 0.3 apart, right? Just go down by 0.3. So it goes 4, 7, 1. 0.4, 0.3 more is 0.7, 0.3 more is 1. Just bad luck. There's no reason why they should be distances exactly the way they are. Well, actually there kind of is when they think about how these things formed. Why are we close and why are the other ones far? There's astronomers of all kinds of reasons, and planets, we talk about that. But still, it's still kind of random. 0.4, 0.71. Then Mars is 1.5. Okay, as soon as we after Earth, the numbers get really nice and pretty, nice and rounded, like 1.5, right? That's pretty good. 1.5 is not 1.36, 1.5. That's a good number. Venus is about 5. So, Jupiter. Jupiter is about 5 AUs away, 5 times further from the sun than the Earth is. So that works out well, right? There's a 1 for the Earth, a 5 for Jupiter, and Mars is in between at 1 and the 5, right? Just put a point in between. So the 5 for Jupiter, the 1 for Earth, you know, it kind of works. You can memorize that. Now, Saturn is about 10. How lucky is that? Again, they're not exactly 10. It's like 9 point something, but close enough. So Saturn is 10. Uranus is 20. Believe it or not, Neptune is 30. And I'm going to put Pluto here because they didn't. Pluto is 40. And Pluto is really small. Okay, that's pretty amazing. I mean, 5, 10, 20, 30, 40. That's like so easy to memorize, you just have to. It's just screaming out to be memorized. It's so cool. Now again, it's not exactly, but really, really close. So in AUs again, in distances from the Earth, those are the numbers, and it makes a lot of things really easy to work with. Like, how long does it take light to get to Jupiter? Well, from the sun, well, it's 5 times more than Earth. It takes 8 minutes to get to Earth, so about 40 minutes to get to the sun. Okay, so let's say we send an astronaut to Jupiter, and you want to talk to the astronaut. Well, it's going to take about, since they're 5 times further from the sun than we are, but let's say we're here, right? We're at 1, they're at 5, so maybe they're 4 AUs away, so it's going to take us 32 minutes. So you talk to your family member in Jupiter, and you send the message, they hear it 32 minutes later, they send you back something to another 32 minutes, it takes over an hour. Okay, and then Pluto is 40 times further away. It takes 320 minutes. What's that, like 5 hours or 5.5 hours to talk to somebody on Pluto? So by knowing these numbers, you kind of get some idea about traveling in the solar system and how to communicate with spacecraft. When they have a spacecraft way out here around Saturn, they want to tell it to do something 10 AUs away, they got to tell about 80 minutes, 10 times 8, about 80 minutes ahead of time. So you got to think way ahead of time. You can't tell it to do something right now. You got to tell it to do something right now, and it does it in 80 minutes. So knowing these numbers really helps you think about distances in the solar system and what it takes to send out spacecraft and all that kind of stuff, which is why it's kind of fun to know. Okay. The other thing you can also think about these numbers is how bright the sun is. The sun's brightness goes down by distance, right? Obviously, the further away you are from the sun, the less bright the sun is going to look. So we know how bright the sun is on Earth. You look at it, it's pretty bright. If you go to Jupiter, it's 5 times further away. It's actually, the sun will look 5 times smaller. Okay, so I'm going to write this down, so you should be able to do this math. This is easy math. So from Jupiter, it's 5 AUs. The sun is 5 times smaller. You look it up in the sky, it'll look 5 times smaller than you usually do from Earth. So if you go to Jupiter, you look at the sun, oh, it looks smaller. Yeah, it's 5 times smaller. On the Earth, it's about 1/2 degree wide, or 0.5 degrees wide. So if you look at a protractor or something, if we look at the Earth, look at the sun from the Earth, okay, there's the sun, here we look at it, that angle it makes is about 0.5 degrees. Or you point to the top of the sun, point to the bottom of the sun, it's about half a degree, 0.5 degrees. Again, is a good number to know. You should know that number. Half a degree down. Oh, and by the way, by luck, the moon is about the same size. The moon and the sun in our sky are about exactly the same size. That's why we have total solar eclipses, and the moon is slightly bigger. It just covers the sun, just barely, and not for very long. Just by luck, our moon and sun are half a degree wide. Now, on Jupiter, it's going to be 0.1 degree wide, right? 5 times smaller. And the dimness, or the brightness of something goes by distance squared. Okay, so it's 5 times further away. We square 5, so 5 squared, which is 25. So it's 25 times dimmer. So a sunny day on Jupiter is 25 times less bright than on the Earth. You go out to get a tan, to get some warm sun on Jupiter, and it's 25 times less warm. That's not very bright, right? That's not very warm. It's cold on Jupiter. The sun is pretty weak on Jupiter. Let's go to Neptune. On Neptune, the sun is 30 times smaller, and 30 times 30, right? 30 squared, which is 30 times 30, which is 3 times 3, 9, and 2 zeros. So it's 900 times dimmer. I mean, the sun is just a bright star. If you go to Neptune, the sun is just a bright star. It's not that bright. Pluto's even worse, 40 times, 1600 times dimmer. If you have solar panels, you're not going to make much electricity. The sun is like it is at 5 o'clock in the morning or something. I mean, it's very, very dim. So again, just by knowing these numbers, you can figure out all kinds of things about traveling in the solar system. So it's good stuff to know. Okay, I'll stop this video here. You can write all this stuff down if you haven't already. Good stuff to know for the rest of your life. Just kind of fun stuff when looking at the solar system. And I'll talk about some other stuff in a different video. So thanks for listening. Hope I'm not too boring. Hope this is fine. I know my face is kind of dark there, which, who cares? It's about looking what I write at. But, and I'm practicing looking at the camera, not like at myself, right? So then it looks like I'm looking at you. I'll get better at this. All right. Thanks for listening. I won't take up your time anymore. Bye, guys.